Okay, good morning, everyone. I hope the Laker fans out there haven't been producing too much glucocorticoids these days, being a bit stressed out with what's going on right now. And the Warrior fans, of course, have the opposite effect. I mean, that big win last night. Reminder, office hours, Monday noon to 1, Thursday, which is tomorrow, 2:10 to 3 o'clock. And also, there's been some good questions by email, so if you guys have email, specific questions by email, that's totally fine. I like that. So today we're going to do stem cells, then kind of go through development a little bit, gastrulation, organogenesis, morphogenesis, and if we have time, I hope inductive signals, and the questions on page 66. Hopefully you guys are trying the questions in the reader as we're hitting the different sections, because it should give you a sense of how well you understand it, and give you a sense of what I'm thinking about also. Okay? All right, brief review. From the secondary oocyte after fertilization events, you get a zygote. You then get a series of cleavage reactions, importantly up to the 8-cell morula. And these cleavage reactions are partitioning of the cytoplasm, but the nucleus undergoes mitosis. The cells are called blastomeres, and up to the 8-cell morula, every blastomere is absolutely identical. And there's a big issue in terms of twins, identical twins, as we talked about. It's a very important issue in terms of stem cells, which we'll talk about today. There's a compaction. About day 4, you get a compacted 8-cell morula. About day 7 or 8, you get a blastocyst, and that's comprised of an inner cell mass, which is also important in terms of stem cells. We'll talk about. I'll leave these two boards up for a while. Then there's a fluid-filled cavity called blastocele, and surrounding it is a trophoblast. There's about 100 cells there, approximately. And then a few days later, there's an implantation. The inner cell mass becomes the epiblast plus the hypoblast. We'll expand on that slightly today. You form the placenta, which is both maternal and fetal tissue. The production of the first hormone from the placenta, HCG, human chorionic gonadotropin, that keeps the corpus luteum alive. It is also the basis of pregnancy tests, and it's also the source of morning sickness. So as you can tell, it does a lot of stuff. We talk about twins. Know the difference between fraternal, identical, and mirror image identical twins. It's based on different aspects of the reactions I've shown on the board there. And then during pregnancy, the main pregnancy hormones that you guys need to know about are HCG, estrogen plus progesterone, prolactin, and chorionic somatomammotropin, CS. By the way, I will not be asking for acronym definitions on the exam. If something involves CS, I'll say chorionic somatomammotropin along the lines there. Okay? Nor will I be looking at spelling aspects of either, such as glucagon versus glucocorticoids versus glucose. Okay? It's easy to mix those up sometimes if you're writing fast. Anyway, there'll be none of that. During the trimester, there's different hormonal milieu during the trimesters. HCG is only around for the first trimester, and as you can imagine, morning sickness is only around for roughly the first trimester. You can ask your moms about that. And then later on, there's estrogen plus progesterone. There's a lot of it, and each of those has specific roles on the mammary gland, the anterior pituitary, and you should sort of understand those relationships. Labor hormones, I didn't quite say it. I said it, but I didn't really have it on the board, so now I have it on the board. And that is estrogen through the estrogen receptor induces the expression of the oxytocin receptor in the nucleus. Estrogen receptors are transcription factors, regulate gene expression. This is what it does. And then the oxytocin comes from the posterior pituitary, prostaglandins come from the placenta. And together they provide the positive feedback during contractions and labor. 2 points. One is oxytocin receptor and prostaglandin receptors are both 7-pass transmembrane receptors, but their target enzymes and pathways are different than glucagon receptor. Therefore, they do what they do during labor, and glucagon does what it does for glucose homeostasis. So there's a whole bunch of 7-pass transmembrane receptors out there. They have different effects because of different target tissues and different downstream signaling components. But I just want to bring it up as yet another example of that. And also, there's a question about what else does oxytocin do. It does has a lot of other effects in males. Is involved in muscle contractions during ejaculation in males. It is thought to be. So it definitely has a role in males. You do not need to know that factoid. You can read about it. But what you need to know is oxytocin is involved in labor. That's the main one I'll have you guys remember. Okay? Questions? Yes. Say it louder, please. It is thought to be, because it's involved in muscle. It's involved in female orgasm also. It's probably yes, because it's involved in muscle contractions, which are involved in both males and females. But there's other hormones involved. It's not the only one. But it is given the nickname, quote unquote, the love hormone for exactly those reasons. Okay? But it does other stuff in the body also. But you don't need to know that. I mean, again, feel free to read about it, but know its role in labor. Because if you know its role there, you can kind of figure out other areas that's important. Okay? All right. Any other questions? All right. Good. So now we're going to talk about stem cells. This is an interesting area both from a scientific and a political side, and therefore I think it's important to discuss it in some depth with you guys. And because of every other day you probably read something about stem cells in the newspaper. So the basic concept here is you have a stem cell. The idea is it can differentiate into other cells, but it does two basic kinds of properties. It has a concept of self-renewal, so it's mitosis, and you get more stem cells which are undifferentiated, or it can differentiate, which is specialization, into other cells and tissue types. And it does this. It's not totally clear. This is one of the big areas. There's various signals. Put this in quotation marks, meaning it can mean anything. Everything from gene expression to hormones to cell signaling components, anything you can think of that can manipulate the differentiation of a cell. And the big push right now is to figure out what are the signals that can convert a stem cell into a specific differentiated cell type. Because it's easy to conceptualize that the signals that go to a liver cell is quite different than the signals that go into an intestinal cell or a nerve cell. Because those are very different kinds of cells. And that's the big push right now in the field. There has been some progress, and part of the progress is thinking about the different types of stem cells. So one kind of stem cell is called totipotent. Totipotent stem cells can differentiate into all cell types, both embryonic and extra-embryonic. So for example, in the blastocyst, the trophoblast will be considered an extra-embryonic tissue because it doesn't become part of the embryo. Okay? And in the mammalian cells, let's just stick even with humans, the only source of true totipotent stem cells is everything from the zygote to the 8-cell morula. Okay? Those are the only source of totipotent stem cells. Makes a lot of sense because what we say about the blastomeres up to the 8-cell morula, they're absolutely identical. And secondly, if one breaks off, you can get an identical twin. So it makes sense that those would be totipotent in their stem cells. And in terms of the political side, these are very important cells to think about. But generally speaking, what you want to use stem cells in medicine for is someone who's obviously living, an adult, kid, whatever, who then wants to correct some sort of genetic defect or disease that they have. So you don't care if a stem cell makes an extra embryonic tissue. All you care about is making specific cells and tissue types. Does everybody see that? So although this is interesting and useful, it is slightly less important than all the issues with the next class of stem cells, which are called pluripotent. And these stem cells make most embryonic tissues. Okay? They do not make the extra embryonic tissue, like the trophoblast, but they make most of the embryonic tissues. And the biggest source of these is the inner cell mass of the blastocyst. So the inner cell mass here of the blastocyst are pluripotent stem cells. And a lot of investigations, in fact, use this, and we'll hit that again. Now, there's several sources of pluripotent stem cells. One, and these, by the way, these are called inner cell mass. The other name given to this is ES cells, or embryonic stem cells. So you'll see in the newspapers ES cells, right? What they're referring to is the inner cell mass of the blastocyst is the source of these ES cells, or embryonic stem cells. This is where a lot of the attention is being played. And that is clearly one source of pluripotent stem cells. There's two other sources that are giving a little bit of attention, not as much. The other source is embryonic germ cells. So these are the precursors for the gametes. Okay? And these are obviously diploid cells, but these are definitely pluripotent. These are harder to get, and therefore not as much attention being played. But you never know. Sometimes, again, depending on how the signals work out, what these cells can get into, maybe an embryonic germ cell can only go to a certain lineage that a regular pluripotent cell can't or has trouble doing. So you never know where a good source of cells comes out of it. Now, another source of cells that are clearly pluripotent, or probably won't be used for very much in terms of tissue differentiation, are embryonic carcinoma cells, which are tumor cells. What these are is fetal gonadal tumors. Fetal gonad tumors. And these are definitely a source of pluripotent stem cells. However, they're probably not being thought of being all that useful necessarily. Okay? Any questions to that point? Most of the political controversy involves pluripotent stem cells, which we'll get back into it. But yes, question. Yes, we'll talk about that. It's not happening in humans, but it's happened in mouse. And we'll talk about that. That's called reprogramming. Okay? Very important issue we will just briefly touch on. If I don't answer your question, answer it again. Ask it again. Okay? Or if you want to answer it too, that's good too. Okay? Other questions?
What about the...
Wait here first. Your name, please? Okay. If you ask 4 or 5 questions, I'll ask you what your name is. We'll get to that. Okay, what self-renewal is basically the cells mitose, but they maintain their property as a stem cell. That's all it is. The harder part is getting the signals to make it differentiated. So the part where all the attention is, it's pretty easy. Nothing's really easy. It's straightforward to take a stem cell and keep it growing. Mitosing. What's harder is this part. Finding the right signals to produce the right cell types. And that's where 99% of the research is right now in terms of what they want to try to do. Find the right signals for the right cell types. Okay, question here. Yes, we'll get to that. They've done that. That's actually the next topic. You got a question also?
Are there also stem cells in the umbilical cord?
Are there stem cells in the umbilical cord? Yes. There are stem cells everywhere. And what these kind of stem cells are, in fact, as we all sit here together, we all have lots of stem cells. These are called adult stem cells. Okay? Umbilical cord has it and so forth. And these adult stem cells are of 2 general but related classes. These are called multipotent. And I also consider part of the same kind of cell, unipotent stem cells. These cells have a restricted differentiation in that they only go into a limited number of cells, of cell types, I should say. As you can imagine, by the definition, unipotent stem cells only go to one cell type, right? Unipotent. So a good example of a unipotent stem cell would be like a muscle stem cell. Goes into muscle cells. And that's a good example biologically on these adult stem cells. So these are unipotent. And a good example of a multipotent stem cell is bone marrow stem cells, which we'll talk about next week a little bit. These guys can differentiate into the myeloid and the lymphoid stem cell cells, which then together give you your blood cells. So it's a very restricted differentiation profile. Again, like I said, these are in adults. And in adults, they've been able to do a little bit of figuring out some of the signals. So what they've been able to do, I think this relates to the question just before, it's been shown that you can take, the idea is to be able to take, say, a damaged cell or tissue in the adult, patch in some stem cells and get it to work again. And they've had some limited success with spinal cord injuries. That they can patch in stem cells and get the spinal cord to be normal. In mice, it works really beautifully. It's a great experiment. I think Amgen is the company that did it. But they had partially paralyzed mice. They gave them actually human stem cells, and the mice were fairly normal within a few weeks in terms of their walking ability. Okay? There's also been some areas in eye diseases where they try and put in stem cells. And there's some experimental methods that are working along these lines. Okay? So there is some successes along these lines. There's been in the cancer area lots of successes. For people with leukemia, what you do is you take out the bone marrow cells and you put back somebody else's or relative's bone marrow cells. What you're putting back are the stem cells, which then differentiate into cell types, and you get your blood cells again. In this way, you get rid of the cancerous or leukemic cells, and now they're not producing normal cells. So that is a form of stem cell therapies. This is all because of adults. Yes?
So by putting them in that environment, putting stem cells in like spinal cord or whatever, is that what gives it a signal?
Yeah, the very good question. The question is, if you put the stem cells in the correct environment, does it have a signal? The answer is yes, because it works. We don't quite know what those signals are. We know what some of them are. We don't know what all of them are. What you like to do is say, have a cookbook kind of formula, right? Some of you guys going into medicine might even have this in 10, 20 years. You have a certain disorder or a defect, and you say, we need to generate some more cells. Here's a stem cell. We add X, Y, and Z. A week later, transplant them in. You got your tissue back. That is where it's going. And you guys may see that. To some extent, it's going on now. But the amount of information has been exponential on this. It's a very interesting area. Yes? Again, what's involved in differentiation? Whatever these signals are. Okay, because I can take cells of any sort, put in certain genes, and get them slightly different cell type. People can do those kinds of manipulations. But how do you do it in a way that's a permanent change? And how do you take an undifferentiated stem cell and give it the right signal to not only go to a liver and intestine, but maybe a nerve cell or a tendon? And by the way, that's one of the new, there's a lot of sports injuries in tendons and ligaments. One of the new experimental approaches they're using is trying to put in stem cells to regenerate tendon injuries, things of that sort. So there's, because anybody who skis, by February, March, there's a whole bunch of you guys out there with crutches and things like that from skiing injuries. And it happens enough that there's a lot of people interested in it. Yes? Yeah, well, the animals that can accept human cells tend to be especially immune deficient. Normally, if you take like for example, in my own lab, we grow human tumors in mice, but those mice have an immune deficiency that allows different species to grow. It would not work for humans. The idea is to get a human stem cell differentiated into a human tissue. And a lot of the attention are these adult cells from multipotent, unipotent stem cells, because you can take them from the other advantages. You can take a stem cell from yourself, change it, put it back in, so you don't have immune problems, immune recognition problems. So it's a very productive area right now in science. Now, the other area is with cancers. Put this here. Cancer stem cells in adults is a big issue. So if you think of a tumor of a certain phenotype, say breast cancer, which is one of the ones that we work with in my lab, you have this stem cell, and you got the tumor growing around it. This will be the tumor. And say you get diagnosed as an estrogen-responsive breast cancer, so it's estrogen receptor positive, of which about 60 to 70% are in early stage diagnosis. You then treat with tamoxifen, which is an estrogen receptor antagonist. Remember we talked about that a long time ago, like 3-4 lectures ago. Tamoxifen, you kill all the cells, anything that's estrogen receptor positive, and what arises out of that are a little bit of stem cells that now differentiate into estrogen receptor negative cells. And what grows out of that, a little X here, what grows out of this is another tumor. Here's a tumor with some stem cells. Stem cells are a very minor part of the tumor that are now therapy resistant. Because what happens is the signals are there, or the stem cells are already there, there's several kinds of stem cells, that it survives the treatment because it does not have estrogen receptor. And then what grows out of that is an estrogen receptor negative tumor, which is now no longer responsive to tamoxifen. And that usually happens in patients 3 to 6, 7 years after the initial treatments. That's part of the reasons why tumors reemerge, is because the stem cells, you kill off everything except for a few stem cells, over the course of a few years, the tumor grows back, but it's now resistant to the therapy. Because the property of the stem cell is different, because it now has a different phenotype due to whatever signals are there. People don't know what those signals are. So there's a lot of attention being played to targeting the stem cells in the tumors for new kinds of cancer therapies. And again, you guys will probably see this, those of you getting into medicine in the next 10, 20 years. That's one of the pushes in cancer biology, is to target the stem cells. Okay, questions on this? So I'd say right now the bulk of the successes have been with the adult stem cells, because they're already designed to go in a certain direction in their differentiation. There's been less so information on the pluripotent and totipotent stem cells. Okay?
So there's no estrogen receptor, then I mean.
Oh, because the cells grow. The question is, how does it survive not having estrogen receptor? They grow in the absence of estrogen receptor. They have other pathways that are activated that don't need the estrogen receptor. And that's what happens. A lot of women that are on tamoxifen, it extends the lives of many women, but 5, 6, 7 years later, tumors can reemerge. And a lot of times they are estrogen receptor negative because of this. Okay? There are other therapies now. Yes? Pardon? It is thought, the oral cancers from stem cells, it is thought that that's the case, that normal stem cells can then mutate or change a little bit and then become cancer. There is some thought to that. Not everybody believes that. I'm on the camp that says it's likely to be the case. That what happens is these stem cells acquire a property that's called tumor initiation. So not all stem cells can make tumors, else we'd be just chock full of tumors, right? Because we all have stem cells in pretty much in every tissue. But these cells, these particular stem cells, acquire a property called their ability to initiate tumors with very low cell number. And so the key is to try to target those guys before they form the tumor. If you get cancer at an early stage, it's a lot probably easier on the patient than at a later stage. Easier to detect. Yes, very good question. On the brain? Yes, the stem cells. I would say virtually every organ's got stem cells. Yes. Not a lot of them. I would say, like, for example, if I know more about the breast cancers, in a typical breast cancer tumor, it's about 1% stem cells. And I don't know what the numbers are for brain or neural tissues. Actually, neural-related stem cell work is there's a lot of people working on that. It's a very interesting area. Okay, so what about the political side of this whole thing? Well, here's part of the issue. And that is, as the concept of in vitro fertilization got going, the issues are you can develop and get lots of stem cells. So what you can do in vitro fertilization, you can go from the zygote to the 8-cell morula to the blastocyst in vitro. Okay? And what does the blastocyst have that relates to stem cells? The inner cell mass, right? And so the political controversy is here you're sitting with a blastocyst. And some people say, well, this can become a human if we can't do anything with it. Or shouldn't do anything with it. But what you can do with it experimentally is you can take the inner cell mass. Let me just put it here. So the inner cell mass, and in vitro, what you can do is grow the cells in vitro. So I see them as inner cell mass cells. You can grow them in cell culture. And what they're doing now is trying to say, let's find the right signals, genes, whatever you want, and have these guys differentiate into a specific cell type. And then take these cells and go back into the patient. And I'll put this in quotation marks because this has not been done yet, particularly. So the point is, this is the political controversy. It's important to realize the potential power of the inner cell mass cells, because these guys can differentiate in theory to virtually any embryonic cell. And very straightforward. You can grow these. In fact, there are undergraduates all over the country growing inner cell mass cells in certain labs in culture, giving them signals, and you can go back into the patient. And that's the whole ballgame. Finding the right signals in vitro, and then patch these back into the patient in vivo. That's where it's all at right now. Up to this point here, it's pretty straightforward.